We want to shift gears a little bit from the last couple of chapters and talk a little bit about energy rather than matter, because energy is going to govern how and if matter changes. So we want to define a few terms first off. Energy is the capacity to supply heat or to do work. So anything that moves has to have energy associated with it. Kinetic energy is the energy associated with motion, and we can calculate the kinetic energy of a particular particle or item by squaring its velocity, multiplying that by its mass, and then dividing that quantity by 2. Potential energy is energy that is stored and hasn't been released yet. So for example, if we set a ball at the very top of a hill, it has potential energy associated with its height. And a slight little push can get it rolling down the hill, and then that potential energy would be converted to kinetic energy. And that brings us to the law of conservation of energy, and that is the idea that energy can't be created or destroyed. It can only be converted from one form to another. Kinetic energy can be converted to heat. Either one could be converted to potential energy. Potential energy could be converted to either one. And so all energy is energy that has always existed. It is just being converted from one form to another. Thermal energy is the kinetic energy associated with molecular motion. So your hand is warm because the molecules in your hand are moving around and vibrating more quickly than someone whose hand is cold. Temperature then is not really a measure of heat. It's the measure of the ability to pass heat, to distribute heat. But a better definition for temperature is the average kinetic energy of the molecules in an object. Heat then is the amount of energy that is transferred from one object to another when they come in contact with each other as a result of their difference in temperature. And chemical energy is energy that is stored, potential energy that's stored in chemical bonds. So for example, sunlight shines down onto the earth, a tree absorbs that energy and uses it to make sugar molecules or starch molecules or cellulose molecules that become the structure of the plant. And then later, if that plant is a tree, we cut that tree down. All of that energy is still stored in those molecules. And we use that tree for firewood. And when we burn the tree, that potential energy is released as heat energy. So that's chemical potential energy. All right, so the first law of thermodynamics is what a physicist would call the law we introduced a few minutes ago, and that is the law of conservation of energy. So if we're going to use physics terms, we'll call that the first law of thermodynamics. So if we have a system that's completely isolated from its surroundings, then the energy of that system is constant. The energy inside of that system can change forms, but it won't change amount, total amount. A non-isolated system is a little bit more complicated, but for a non-isolated system, the change in energy for that system is going to be equal to the final energy contained by that system minus the initial amount. So for example, the picture system in this picture, if we have methane reacting with oxygen to form carbon dioxide and water, that's going to give off 802 kilojoules of energy per mole of methane, because that is going to be energy that is released. So if we have a system that's here where some reaction is going on and energy is able to escape, say, as heat, then that heat that comes out would be the change in energy for that system. Now, a state function is a property or a function whose value depends only on the present state or the condition of the system, not on the path to access that state. So for example, if you live in Boston and you're going to travel to Castroville, California. That's about 3,000 miles from home. How far you are from home is a state function. It doesn't matter how we got to Castroville. We are 3,000 miles from Boston. However, the amount of energy it took or time it took to get there is not a state function. It depends on what path we traveled. This way, by way of New Orleans, and then up this way and then across, is a different amount of time and mileage than going this more direct route. And so money spent or work expended or gasoline burned are not state functions, but how far you are from home is a state function. Now, if we talk about work, work is force times distance for moving an object. You get the same exact units if we multiply pressure by volume. So expansion work, blowing up a balloon, for example, work is going to be the amount of pressure that's used times the change in volume. And in order to keep our signs working, we put a negative sign here. So work is negative pressure times change in volume as far as work done on the system. So collapsing work, a balloon being pushed down or a tire being pushed down or squeezed, that would have a positive sign because the change in volume would be negative. And blowing up a tire would have a negative amount of work if we're considering the tire the system that we're interested in. So for example, let's calculate the amount of work, and work has the same units as energy, in kilojoules, that's done in a reaction in which the volume of the container of the reaction expands from 12 liters to 14.5 liters against an external pressure of 5 atmospheres. So you think about this, we have some sort of a gas generating chemical reaction going on inside of a balloon. And as a result, the balloon expands from being 12 liters to 14.5 liters. The balloon gets bigger. So the balloon gets 2.5 liters bigger. So let's take a look at the solution to this problem. We just said work is negative pressure times change in volume. The pressure is 5 atmospheres. The change in volume is the difference between the final volume and the initial volume. That's 2.5 liters. So we get negative 12.5 liter atmospheres. And then we look up, and I don't want you to memorize this just yet, but we look up a conversion factor for joules to liter atmospheres. And it turns out that conversion factor is 101. So there's 101 joules in what we call a liter atmosphere. And then there's 1,000 joules in a kilojoule. And so we have our conversion factors to convert from liter atmospheres, which is a work or energy unit, to kilojoules. And this comes out with only two significant figures, to negative 1.3 kilojoules of work done on the system. Now, what kind of a reaction might cause this kind of work? Let's say this green highlighted area is some methane and some oxygen. Specifically, let's say it's 1 mole of not methane, propane gas, and 5 moles of oxygen. So that's what's in here. And there is a certain pressure holding this piston down. Now, if the pressure stays the same, but we light a little spark in here, and we have the temperature warm enough that water would be gas, then we get that chemical reaction going where methane reacts with oxygen. Propane reacts with oxygen and burns to generate CO2 and water. And when we balance the equation, we see there's 6 moles of gas on the left and 7 on the right. So that means that this container, if we keep the pressure constant, is going to expand by some distance. And the amount of work that gets done is going to be force times distance, or it's going to be the negative of the pressure times the area of the circle times the distance, because volume of this area of this part of the container is the area of the circle times the height of the cylinder that changed. And so that's how we calculate work in chemical reactions that generate gases. Now, the total energy change for a process is going to be the amount of heat that's transferred plus the amount of work that's done. And we already have an expression for work, negative P times delta V. Q in this expression then is the amount of heat that gets transferred. So delta E is going to be Q if there's no work, and there's going to be no work if the volume stays the same. So if we do a reaction in a very stiff, unflexible container that doesn't expand, then the pressure might go up if we generate more gas. But since there's no delta V, there's no work. Now, if we have constant pressure, then generating gas is going to expand the container. We only have constant pressure in flexible containers like tires and balloons. And so pressure is held constant, volume can change, and we can have work that happens. And so the heat energy and the total change in energy aren't necessarily going to be the same. So whether work is a factor in the heat versus energy equation is determined entirely by whether the container is of a fixed volume or not. Most books, instead of calling heat Q when we're talking about constant pressure situations, open containers and flexible containers, instead of calling that Q, they'll call it delta H. And the technical word for that change in heat at constant pressure is change in enthalpy. So delta H stands for enthalpy. So that'll be a good vocabulary term for you guys to make sure that you're aware of. All right, so let's take a look at one more practice example before we run out of time on this video. Nitrogen reacts with hydrogen to make ammonia, and the delta H, the change in heat for that process, is negative 92 kilojoules. What is the value of delta E in kilojoules for that reaction if it's carried out at constant pressure? So that means we can have work happen. And the pressure is 40 atmospheres, and the volume change is negative 1.12 liters. So delta H, based on the equations we just learned, is delta E minus work, or plus P delta V. We can rearrange that to solve for delta E, since we know delta H and we know the change in volume. So delta H is negative 92.2 kilojoules, which means we need to get this work term in kilojoules. So I've got the work term spread out inside of these brackets. Work is pressure, which is negative. Let me fix this. Hold on just a second. That's better. Had a unit error here. The pressure is 40 atmospheres. The change in volume is minus 1.12 liters. So now we have liter atmospheres. And on the previous example, we learned how to convert from liter atmospheres to joules, and from joules to kilojoules. This is a conversion factor I would give you on the test. This is a conversion factor I would not give you. But if we multiply 40 times negative 1.12 times 101 times 1 over 1,000, we'll get a negative number, but then that's minus a negative 4.5. And so the total delta E comes up to negative 87.7 kilojoules. The two examples we've worked in this video are worked in your textbook. If you want to take a little bit closer look at them, and we'll try some others in class together.